Okay, so finally we've talked about what it means to be meromorphic, or holomorphic at infinity and holomorphic to infinity. It turns out meromorphic functions are the same thing as maps to P1, holomorphic functions to P1, and that and things like holomorphic functions on all of P1 have to be constant. And this follows from the fact that every bounded entire function must be constant, because if it was holomorphic on all of P1, then it must be bounded and had to be constant. Okay, so now I want to talk about holomorphic maps from P1 to P1. So we're going to kind of combine these two things together. Okay, so let me just recap again what we've done so far. So if we take a meromorphic function, right? So we said that f was holomorphic at infinity, right? This thing corresponded to the condition that f of 1 over zeta was holomorphic at zeta is equal to 0. So again, we're using holomorphic analytic. This means it locally has a power series. In terms of the picture here, here's where you have P1, and we have our point 0 here, and we have our point infinity here. And what's happening is that infinity in this case is mapping to some finite point here, f of infinity, which is some point here. Okay, so this is one copy of P1, this is another copy of P1, but the point at infinity maps to some finite point here. Similarly, we said that f was holomorphic to infinity at some finite point z0. This condition was equivalent to the condition that this reciprocal was holomorphic at z is equal to z0. So again, locally analytic at z is equal to z0. So here's the picture. We have P1, and we have some finite point z0 here. We have another P1 here, and f is a map between these two guys. And so what this guy does is it maps this guy to the infinite point up here. Okay, so and we check this in a neighborhood around infinity. Okay, so so the idea now is to talk about maps P1 to P1. We combine these two conditions. Combine these two conditions. Okay, and we combine these two conditions, and sometimes we'll have infinity going to infinity. All right, so great. And so what do? We say that f is holomorphic to infinity at infinity if and only if 1 over f of 1 over zeta is holomorphic at zeta is equal to 0. So again, we're saying that this has a local power series here. And so the picture, so you have one copy of P1, we have our point at infinity, here's our point 0. We have another copy of P1 here, and this guy is mapping to this guy. So we have some neighborhood here, and it's going to some neighborhood here. Okay, so this is our map f. F is taking infinity, like so. So this is one extra condition. So so let's make some notation. So the collection we will denote the collection of such maps, of maps holomorphic from infinity to infinity, as whole P1 to P1. Okay, so this is the only condition we had. So again, not all maps will map from P1 to P1, but we just checked that they're holomorphic, or that they're holomorphic to infinity, or that they're holomorphic at infinity with a finite value. Okay, so we just combine these three things to get all these functions. So it needs to be holomorphic at every single possible value, input and output. Okay, so let's do an example. So if P of z is a polynomial of degree d, then we notice that 1 over p of 1 over zeta here, so this thing looks like zeta to the d, p of 1 over zeta. Okay, so this is, so now this thing here is holomorphic near zeta is equal to 0, so this thing is an example of a map of some function with f of infinity is equal to infinity. So we don't necessarily need f of infinity to be equal to infinity to be in here, but this is just one example where we have to use this extra, the combined condition to infinity at infinity. Okay, so now I'm going to go and prove the thing that Veronica had mentioned in class. Okay, so so a function f in mer C defines a holomorphic map so from P1 to P1 if and only if let's say f is a rational function. Say f of z is p of z over q of z, where p of z, q of z are polynomials, and q is not 0. Okay, so the holomorphic maps from P1 to P1 are just the rational functions. So, okay, so let's try to give this a notation, i.e. whole P1 to P1 is CZ. Okay, so here's the proof, and we're going to do it in two cases. So let's start with f, which is a meromorphic function on C, and let's say it's holomorphic at infinity. So if f infinity is not equal to infinity, okay, this is the first case, and then we'll do the other case where it's equal to infinity. Okay, then by definition, g of zeta, which is f of 1 over zeta, looks like zeta to the m naught h naught of zeta is analytic at zeta is equal to 0. So So by definition, it's going to be analytic at 0. So then we write this. So this guy here, this is not 0, and then this is just the comes from the factorization of analytic functions. It's just the comes from factorization. Okay, so this tells us that this guy, so this has no poles by analyticity for this guy less than r, for some r, right? And this tells us that f of z has no poles for, this guy bigger than 1 over r. So we just flip this. And so this means that there exists a polynomial that can get rid of all the zeros. So we take all the zeros that this guy here, so all the zeros with, so this guy has no poles. For here, so we just we multiply out by all the poles that it would have, since there's going to be finitely many due to isolation of poles, and hence it's entire. Okay, so also this tells us, since we know P of z is holomorphic at infinity to infinity, is holomorphic at infinity to infinity. Okay, so this means that 1, we have just to flip twice, this guy is holomorphic. So this guy we can write in some way. So this guy is analytic / holomorphic near zeta is equal to 0. Here, this guy here is. Okay, and yeah, so this guy's analytic and not equal to 0. So this tells us that if we bring everything to the other side, 1 is equal to okay, this guy is not equal to 0, which implies that the limit as zeta goes to 0 of this thing this guy, if we just add one more 0, that this is 0, which is the same thing as saying that the limit as z goes to infinity okay, so therefore this thing here, P of z, f of z, is an entire function. Is entire, and little o of z to the n plus 1 as z goes to infinity. So by Liouville's, by the modified version, this guy here is a polynomial. Is a polynomial. Okay, and so we get this whole thing as a polynomial. Okay, so therefore f of z pz is equal to qz is qz over pz, so, and hence rational. Okay, so that was the first case. The first case, what do? We supposed that it was holomorphic at infinity, but it wasn't to infinity. So if f of infinity is infinity, then we're just going to do this thing. So by definition, we're going to do something similar. 1 over f of 1 over zeta. So this looks like h0 zeta, zeta to the m0. So where this guy is not equal to 0. So this is an h0 is analytic. Okay, near zeta is equal to 0. And this is say for this guy less than r. Okay, so we have this expression again. So by definition of holomorphic at infinity to infinity, so infinite values and points. Okay, so this implies that this function okay, so this has a power series, right? All right, so this, by definition, this means that this guy is holomorphic at infinity with non-infinite value. So this is the previous case. Okay, and so by the previous case, this thing must be a polynomial. Sorry, this guy is rational. Which implies that f of z is rational. And we're done.